Day 130, Electrostatics. Homework hints for numbers 21, 22, and 41 from your packet. In problem number 21, you have four charges at the vertices of a square. All the same charge, so a good idea here is to draw this all out. And there doesn't really, I'm just going to give you an outline here. I guess they're 5 microcoulombs each charge. So each charge will be exerting a force on the other three. In other words, each charge will exert 3 forces, but it will also have 3 forces exerted on it, according to Coulomb's law each time. And there'll be a lot of symmetry here. We'll be using this to start the problem, F equals K Q sub 1, Q sub 2, Coulomb's law, over R squared. And you only need to look at one corner because all 4 corners will have the same answer. For example, I'll take the lower right corner. So the 2 charges on the bottom of the square will be repelling each other. You'll be plugging in 5 microcoulombs, and their distance. I'm going to be making up numbers here because I'm not going to do the actual problem for you. I'm just showing you how it is done. But they will repel each other. I can call that F sub 1, F sub 2. It's simply found by plugging into Coulomb's law over there on the right with this particular distance of separation, which I think is 30 centimeters, 0.30 meters. And you'll get a number for that F1. I'm going to make up a number that's not the right number in a minute here. On the right-hand side, you have the 5 microcoulombs at the top, at the bottom, and they repel each other. I'll use blue again. But F, I'm going to call that F sub 3 and F sub 4. They repel each other. I really don't care about F sub 4, but it is equal to F sub 3. In fact, all 4 of these forces I've drawn already are equal to each other because we have equal charges with equal distance between them. Now, however, now the 2 charges kitty corner diagonally across from each other in this setup also repel each other. So what happens here is, in the upper left, that charge will repel to the lower right, but that force is going to be a little bit smaller. I'm going to call that F sub 5 for lack of more creativity, and F sub 6. But F sub 5 and F sub 6 go together as a pair. They'll be equal and opposite. So in other words, in the lower right-hand corner now, there are 3 forces being exerted on that 5 microcoulomb charge. F1 and F3 will be equal to each other, so that's only one computation. But F5 will be a little bit smaller because even though the charges involved are still 5 microcoulombs each, the distance between the 2 corner charges is more than the 30 centimeters. In fact, if you figure out that distance across diagonally, there are shortcuts, but bottom line, it's going to be 30 times the square root of 2. You can Pythagorize it to figure it out, but it's a slightly bigger distance than 30 centimeters, 0.30 meters, when you plug, bigger than 0.30 meters when you plug it into Coulomb's law. So it results in a smaller force, F sub 5. This is a it's a vector problem, and it's a vector problem in which you've got to add the 3 vectors that are pictured here on this charge in the lower right corner. Now there are general ways that we've discussed in class to add vectors. One way would be to take the F sub 5 and break it up into 2 components, which would be a good way to do this problem. However, there's a little trick, if you want to call it, in this particular situation. If you know that F1 and F3 are equal, and this only works if F1 and F sub 3 are equal, if I just look at those 2 charges first, or the forces first, F1 and F5, if I just combine them, add them, F1 will be this way, F sub 3 will be this way. The resultant of F1, F sub 1, and F sub 3 will be diagonally this way at 45 degrees exactly. The nice thing about that is the resultant of F sub 1 plus F sub 3 will be in the same direction as F sub 5, which makes us able to use a shortcut. In other words, if R, the resultant there, is in the same direction as F sub 5, to find the final answer, because I need to combine R plus F sub 5, they're in the same direction, so it's just simple arithmetic. It's not even algebra. So for example, if R, I'm going to make up a number, if R is 6 newtons, let's say, it's not 6 newtons, it's much, much smaller than that. And F sub 5 were 2 newtons, my answer now would be 8 newtons, because 6 plus 2 is 8 newtons, and it would be diagonally outward from the center of the square. You could just say diagonally outward. Basically, that's the idea of how to solve this problem, and the answer will be the same at all 4 corners, diagonally outward, for all 4 charges. All right, those are some hints then for problem number 21. Let me go to the next page. Problem number 22 is essentially like number 21, except for we have 3 charges to start with, all equal in size. And in this case, they're all 25 microcoulombs. So I would hope you're drawing diagrams to solve these problems. Now you have a missing corner here, or a spot, or location, which you're going to put a third or fourth charge of negative 20 microcoulombs. I'll indicate that with blue. So negative 20 microcoulombs. But the problem will be solved the same way as the one we just did. Basically, that blue charge there will have 3 forces acting upon it, but now it's going to be attracted to the other 3 forces, 3 charges. So it'll be attracted to the left, all right? These 2 guys on the bottom here will attract each other, and you can calculate that. You know how far apart they are. You know what the charges are. You just plug into F equals KQQ over R squared. You can call it F sub 1 and F sub 2. I don't care about F sub 1 right now because they're only asking me for the net force on this minus 20 microcoulomb charge. And then it's being attracted up this way. I can call it F sub 3. F sub 3 will also be the same as F sub 1 and F sub 2. I can call this F sub 4. Not important right now. But they attract each other. And then it's also being attracted across diagonally with a smaller force. Once again, calculate the total distance from the upper left to the lower right. It's a little bit more than the given, what is the number given here? 50 centimeters total. So a little bit more than 50 centimeters. A little bit more than 0.50 meters. But that'll be an F sub, say, 5. And F sub 6, which, once again, I don't care about. I'll just draw it, though. And like in the last problem, I would simply just add the F sub 2, F sub 3, because they will come out, since they're equal, they will come out at a 45-degree angle, just like F sub 5 is at a 45-degree angle. So add the F sub 2, F sub 3, get the net force for those 2, and then just add it arithmetically to F sub 5. And the final answer in this problem will be a net force towards the center of the square for that lower right-hand corner charge. Now, however, there's a part B. In part B, they're asking you to, well, starting with the same configuration, you have the 3 given charges at the 3 corners, 25 microcoulombs. But the fourth charge will be placed in the center of the square. All right, I'll indicate that with blue, which is right about here. And on first glance, it might look more difficult, but upon further investigation here, this is going to actually be an easy problem because, once again, that blue charge, the negative 20 microcoulombs, will have 3 forces exerting on it. So starting from the lower left, I can draw the diagram. It's going to be attracted towards the lower left. The difficulty is figuring out how far that is. However, you're going to find out you don't even need to figure out how far away that is, F sub 1, F sub 2, because what's happening here is that charge in the center there, the minus 20 microcoulombs, is also being attracted up to the upper right. I can call that F sub 3 and F sub 4. But what's important here is F sub 2 and F sub 3, which are equal in size because they're equidistant from the 2 corners to begin with, and all the charges are equal. So based on Coulomb's law, F1 will equal F2, will equal F3, will equal F4, and then F2 and F sub 3 will cancel each other out. So you don't even need to cancel all those. If you show the diagram and you show that f sub 2, or just state that f sub 2 equals f sub 3, right, they cancel out. So all that's left then for the negative 20 microcoulombs is being attracted to the upper left. Call it f sub 5, f sub 6. Once again, f sub 6 is the force in question. All I need to do is calculate f sub 6. It's just one straight calculation. Oh, however, you have to figure out how far it is from that upper left-hand corner to the center of the square. Basically, figure out the diagonal of the square, and then take half of the diagonal to get you the distance from the center of the square to the upper left-hand corner. And then you'll just be plugging into f equals k q sub 1 q sub 2 over r squared, and the answer will be then that magnitude directed towards the upper left-hand corner, or towards that 25 microcoulomb charge as shown in the diagram. Finally, problem number 41 on the homework. Some hints here. It's talking about, I believe, the Earth and the Moon. Let's say they are charged. Once again, a little diagram may help. Let's say this is the Earth, and this is the Moon, a little smaller. M for Moon, E for Earth. All right, they attract each other gravitationally, and they're going to ask you to calculate that in the second part here. But let's say that they were charged, and it says that the Earth is charged negatively. Yeah, negatively. And the Moon is going to be charged positively the same amount. So it's going to have a negative charge, and the Moon will be positively charged, so they're going to be attracting each other because of electrical attraction, F sub E, and you're also going to do F sub G, but F sub E is going to be K times Q sub 1 times Q sub 2 over their distance squared from center to center. Now, it says that the Earth has a charge of negative charge because of 1 gram of excess electrons. Now, each electron is 1.60 times 10 to the negative 19th coulombs. And it says I have 1 gram of them. Now, 1 gram of electrons is a lot of electrons. How many is that? Well, 1 electron, or the mass of 1 electron, is 9.11 times 10 to the negative 31st kilograms. I don't expect you to know that. I would give that to you on a test. So if the mass of each electron is that much, and I have 1 gram of them, if you take the big number, the 0.001 kilograms, which is 1 gram, 1 gram converted to kilograms is 0.001 kilograms of electrons, divided by each mass, 9.11 times 10 to the negative 31st kilograms for each electron. That will tell you how many electrons you have. I'm not going to do that for you right now. I am just going to make up a number because I want you to do this problem. But it comes out to be a very, very big number. Let's say that comes out to be 2.7 times 10 to the 9th electrons. That's a number. That many electrons. Well, if I have that many electrons, and each electron is 1.60 times 10 to the 19th coulombs, what you do is you'll take that answer times the 1.60 times 10 to the negative 19th. That's the charge on each electron, and that will give you the total charge you have on the Earth. And once again, it doesn't matter that it's negative. The negative is already taken care of with the arrows in the first diagram because the Earth and the Moon will attract each other. So that will give you a number, the total charge on the Earth. That's what's going to go into Q sub 1. That'll also go into Q sub 2 because it says that the Moon now is going to have a positive charge of that same magnitude. So that will be equal to Q1 and Q2 in that equation at the top of the, Coulomb's law there. The other thing you need to know here is how far apart the Earth and the Moon are. So once again, you need to know the radius from the Earth to the Moon. Okay, Google that. Just go on Google and type in distance from Earth to Moon, and it will be assumed that it's from center to center. That's what they will publish online. Find that. Once again, I don't expect you to know those numbers. I will give those to you on a test. So basically, you're going to just look that up and plug in the other numbers that I just gave you, and that will tell you the force of electrical attraction between the Earth and the Moon if there was that many excess electrons on the Earth or that many electrons missing from the Moon. That's a small amount. It's a gram of electrons. In part B, it's a similar situation. I'll do this in blue. You need to go back and figure out the gravitational force of attraction, F sub g. It's g m sub 1 m sub 2 over r squared. And g, once again, you can look that up. Well, I'll give it to you. G is 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. That's big G. But now you need to look up the mass of the Earth and the mass of the Moon. Mass of the Earth, just Google that. Google, just type in, as you all know, what is the mass of the Earth? Mass of Moon. We actually have this in our notes someplace, first semester. And mass of Moon, you got to look those up. And you'll use the same radius, same distance as you used in part A to figure out the electrical force, because it's always assumed center to center. So you just look those numbers up, plug them in, and see what the gravitational force is. See which force is bigger, the gravitational force or the electrical force, and how much bigger the one force is than the other if they're not even close. Take the bigger force divided by the smaller force and see how many times bigger the bigger force is in this particular situation.